Okay, so on Friday, which seems like it was about 3 months ago, we left our heroes having figured out how to not only find the resultant, but to find the heading for the resultant, using Pythagoras to find the resultant, using tangent to, or inverse tangent to find the direction. Well, now we want to look at going the other direction. So what if we want to take motion that has two component pieces and break it back into those components? This is basic trig. This is absolutely fundamentally basic trig. So in these kind of cases, you're given the resultant, and we want to know what the x and y displacement are. So we always start off by looking at our angle theta, opposite, adjacent. So for any situation, we can say, well, let's see, the sine of theta, and I usually write this all out for myself a couple of times until my brain is really warmed up. Sine theta equals opposite over adjacent. Oh, well, in this case, opposite is delta y, adjacent is delta x. Now I can just get rid of that. Well, I'll just do that. So sine theta equals delta y over delta x. What did I just do? Why don't you people call me on my, yeah, good Lord, crazy person. Hi, happy Monday. Okay, forget everything I said there. Okay, I was going to start the whole recording over, but what the heck, I'll cop. Everybody makes mistakes. Okay, let's review. So, ka, choa, since apparently I need to have that written on every slide. So, sine theta equals the opposite over the hypotenuse. Is that better? That's better. Okay. And in this case, the opposite is delta y. The hypotenuse, of course, is our resultant. So now I can disregard that. So I know that sine theta equals delta y over the resultant. If I want to solve for delta y, it's a pretty simple matter of saying r times sine theta equals delta y. This will become such second nature to you because as we get further in this chapter, as we go into forces, as we go into work, as we go into all of it, you're going to get really used to breaking vectors down into their components, and you're going to use this all the time to the point where you will no longer at some point have to do this step. But for now, you may want to start off doing that step. Okay? So let's do a real life example. Actually, first, before we do that, so this gets us our delta y. If we want to find delta x, we know that cosine tangent is equal to the adjacent, which is delta x, over the hypotenuse, which is r. So we know that r times cosine theta will give us delta x. What you'll start to do pretty soon in problems when you start to list variables is you'll list that expression for delta x. It becomes really important to put those expressions in because you'll use those algebraically to get other pieces of the puzzle. Now let's talk about one more thing. Obviously, it's easy to see that this works for displacement. You take a shortcut, well, how far east are you? How far north are you? Those are your delta x, delta y, your components of displacement. What's often less clear is the fact that we can use this same methodology for other vector quantities. We can use this same strategy for components of velocity, for instance. So let's say you are traveling at 14.9 meters per second at 42.7, what's my heading? North of west. Okay. And what I'd like to know is if this is like a finish line of some sort, and I've decided instead to travel directly west. It's not a straight line, but it's supposed to be. Let's fix that. Then what would have to be my x, my velocity? So in other words, what's the x component of that velocity? Well, this is adjacent to the angle, so I'm going to use cosine theta is equal to, since I have to write ca up there for myself, the adjacent, which is v sub x, over the hypotenuse, which is just the total velocity. What that means is that v times cosine theta will give me the x component of that velocity. So in this case, I have 14.9 meters per second times cosine 42.7 degrees equals v sub x. Let's get a raw number. Okay, so I get a raw number of 10.95022. It goes on and on and on, as many digits as my calculator will give me. I got 3 sig figs, right? Ooh, this is one of those. What is this with 3 sig figs? 11.0. So I have 11.0 meters per second. What's my heading? It's just west, yeah. West is the x component of the velocity. So if that, whatever that line is, that finish line, if your only goal is to get there at the same time as the person going at 14.9 at 42.7 north of west, you can putt right along at 11 meters per second and get to that point at the same time they do. Okay? It's still a vector quantity. Make sure you have direction. Seem reasonable? Okay, let's do the actual problem, and then I'll cut you loose on 3B. Okay, so this is sample problem 3B, which is on page 93. And it just says find the component velocities of a helicopter traveling at 95 kilometers per hour at an angle of 35 degrees to the ground. So here's the ground. Here's my helicopter. Let's see how bad a helicopter I can draw. It's not terrible. I've seen worse. Not much, but I've seen worse. Okay, and velocity is equal to 95 kilometers per hour. Note that I'm putting this picture there. Do a picture. Start these with a picture. These are very, very visual. Now, considering the fact that I'm not solving this graphically, do I have to make my 35 perfect? Nope. Now, am I going to run into sort of cognitive dissonance? Is my brain going to tell my eyes things that I shouldn't believe if I make that my 35? Yes. So try to be reasonable, but you don't have to measure this with any protractor or anything. Obviously, we can see that that's more than a 45, so I don't want to do that. When I'm doing a 35, I basically go, okay, well, that'd be a 45. Okay, that looks like it could be 30. It does not have to be perfectly drawn. So we want the x and y components of this velocity. I'm going to, since I can't be trusted to remember my trig functions on my own, I'm going to write SOHCAHTOA over there. And I'm going to start with my x, in this case, is adjacent. So cosine theta equals adjacent over hypotenuse, which in this case equals v sub x over v. So v times cosine theta gives me v sub x. What is it? So I've got 78 kilometers per hour is v sub x. So that's its, what's the heading on this? Didn't say north, south, east, or west. We don't know. We don't even know left or right. I tend to, by default, draw my angles opening into the first quadrant, but we don't have any of that information to go on. You can write something like parallel to the ground or along the horizon. Those are reasonable, acceptable headings for this. Because again, we don't know north, south, east, or west, and we don't know up or down, or we don't know even right or left. So I'll circle that as 1. Well, now we got to find the y component of its velocity. I'll switch colors just to be difficult. So sine theta is equal to Vy over V. So V sine theta equals V sub y, 95 kilometers per hour times sine of 35 equals V sub y. So we get 54 kilometers per hour. What's our heading here? Up. Up. If it's down, the helicopter's in very serious trouble. And we were told that this was above the horizon. That's where the picture helps you, because you immediately look at that vector and see that the y component of that velocity has to be upward. So we'll write up equals Vy. Okay, questions? This is fairly straightforward. This is pretty easy stuff. So I'll cut you loose to work on 3B, and then if anybody has questions on 3A, 3B, or any of the rest of it, we'll address those.